So we've been talking about Charles Darwin and his book on earthworms, the real title of which was The Formation of Vegetable Mold Through the Action of Worms. Now, Darwin was not the first to write on the subject of earthworms. What makes his work truly germinal is that he so nicely incorporates two major themes of modern scientific inquiry. In essence, he was modeling excellent use of the scientific method, which would be emulated by generations of biologists for decades to come. In the previous video, we discussed his use of hypothetico-deductive reasoning. First, to posit that it was earthworms that caused the gradual bearing of giant stones in stone buildings, with layer after layer of soft earth brought to the surface by the tunneling worms. He supported this hypothesis in two ways: by demonstrating that the earthworm's activity was adequate to account for the accumulation of new soil at a rate consistent with the observed rate of objects sinking deeper and deeper into the ground. Further, he demonstrated that the minerals present in the new soil at the surface matched the physical properties of the substratum underlying the new soil, thereby giving his earthworm hypothesis greater support over the competing hypotheses. Note that there is no proof that Darwin was right about the earthworms causing the slow sinking of buildings and boulders into the landscape, contrary to a belief that's common among non-scientists. Science does not seek scientific proof. This would simply not be realistic in 99.9% of all the things that scientists study. What Darwin did was about all that a scientist can ever do, that is, to establish that a model is the best available explanation for a natural phenomenon. In this case, worm activity is the best available explanation for the phenomenon of things getting gradually buried over time. Now, there's a second little experiment that Darwin performed with the help of his son. This was basically an investigation of whether we could infer any intelligence on the part of a lowly worm. No one would expect that the earthworm would need intelligence in doing what the earthworm does. But now it occurs to me that you might not know exactly what it is an earthworm does, so I'll take a few moments to give you a bit of background. You probably know that earthworms live in the soil, but what do they do there? Well, they tunnel a lot. They create new tunnels by pushing and eating their way through the earth, leaving behind them a worm-sized tube that has walls that are packed and coated with worm slime. These tunnels are the worm's escape route. A lot of the dirt that the worms eat in order to create the new tunnels gets deposited in little piles near the entrance to a worm's tunnel. These are the castings that we talked about in the last video that accumulate as new soil. At night, the worm also forages on the surface for leaves and other litter, and when it finds a leaf, it'll try to drag that leaf backwards into its tunnel. There the leaf will decay right in the worm's tunnel, and the worm has a steady supply of food in the form of rotting leaf material. A foraging worm can drag several leaves into its tube in a single night. Now, if you think about this basic task from a worm's angle, pulling a big, flat leaf into a tubular tunnel is going to present a problem. In pulling the leaves into their round holes, the worms must somehow get them to roll into a conical tube, which can then be pulled into the burrow more easily. Now, the place on the leaf's margin where the worm grabs the leaf will, to a certain extent, determine the relative ease in which the leaf rolls into a tube as it's pulled into the wormhole. If you're talking about a leaf shaped like this will be far easier to pull into the worm's round entrance hole if the worm grabs the leaf by its tip. But besides the fact that the worms are blind and they're doing all this foraging at night when they couldn't see anyways, they are, after all, just worms. They aren't spineless little engineers out with their leaf surveying equipment, and they don't huddle together in little underground meeting rooms to brainstorm and theorize the best way to drag a flat leaf into a round hole. They reach around blindly, and when they find a leaf, they grab it, probably at the spot where they first touched the leaf. Or do they? This was Darwin's question. A very modest question, but one that can be addressed in a perfectly scientific way. If it turns out that worms are displaying some selectivity about where on the leaf they grab, this could require a greater amount of brain power relative to just grabbing the leaf at random. Non-random leaf grabbing could be a sign of worm intelligence, which is something that no one before Darwin had ever suggested or investigated. Okay, so what did Darwin do? Well, for one, he enlisted the help of his son William to go out and collect leaves from the worm burrows and marking on each leaf where was the vertex of the cone. Unrolling each leaf, this would be where the worm grabbed the leaf to pull it into the wormhole. In the first collection, and they did several, but I'll only talk about this one, out of 277 leaves collected, all of the same species of plant, and the leaf shape was similar to the one in my picture, about 80% had been pulled in by the tip. The other 20% had been pulled in either by the side of the leaf or the base. And so basically it looked like the worms were preferring to grab the leaf at a spot where it would be easier to drag it into the hole. Now this was a great starting point for the investigation, but what I've described so far is not experimental in the sense that there's no manipulation of conditions leading to the data that are used to evaluate the predictions. We have the observation that worms are dragging leaves by the pointy ends preferentially, but this isn't quite the same as saying that there was a decision made by the worms based on geometry and ease of rolling the leaf into a tube. For example, one could argue that the chemical cues that the worms used to detect the leaf were different at the tips versus other parts, and worms were using chemical signals to find and grab the leaves. So if it were chemical signals that led the worms to the leaf's tip, then it would not be the case that leaf geometry was part of the criteria used by the worms to decide where to grab the leaf. Darwin's experiment to investigate this made use of artificial leaves that he and his son William made out of paper triangles that were rubbed with animal fat to keep them from turning to mush in the dewy and rainy English nights. The Darwin's triangles were isosceles, and the two like sides were 3 inches in length, and the base of the triangle was shorter. These triangles were marked with equally spaced lines parallel to the base, and this divided the equal sides into 3 zones: closest to the vertex, middle, and closest to the base. Call them zones A, B, and C. The two Darwins put several hundred of these paper triangles out in the garden and collected the data the next morning. In Darwin's reasoning, if the worms were randomly grabbing the paper triangles by their edges, there would be a 1:1:1 ratio of triangles being grabbed in each of the 3 zones. Now, if worms were grabbing at random, but based on the availability of surface area to grab, then Zone C, close to the base, would be grabbed at a rate 5 times higher than Zone A because there's this much more surface area in the basal trapezoid than there is in the triangle at the tip. What the Darwins found was that out of 303 triangles pulled into the burrows by the worms, 62% were pulled in by the tip, Zone A. Darwin inferred that a reasonable explanation for this was that the worms were preferentially grabbing the triangle in Zone A based on geometry alone, since there could be no other basis for the worm's strong bias in grabbing the triangles by their tips. Darwin's investigative method here illustrates exactly the kind of logic that is at the core of scientific experimentation. A lot of people associate science with the use of highly complex technological materials and equipment. This technology becomes falsely equated with the science itself. But no, being highly skilled at using scientific equipment does not make a person a scientist. The fancy equipment may be required in many studies only because that's how the scientist is able to investigate the questions being asked. But if you strip away all the white lab coats and the bells and whistles of the million-dollar machinery used in modern research labs, you still have a core question and a rational and logical process by which the question is being investigated. That's where the science is. That's what Darwin is showing us in this little homegrown experiment from a century and a half ago, before the methods of modern science were analyzed and codified. In Darwin's case, he asked a very simple question. Do earthworms display any intelligence? And through a series of inferences based on observations from nature, natural leaves that had been pulled into burrows, and an experimental design using artificial leaves, the paper triangles, in order to eliminate uncontrolled covariates that occur with natural leaves, he was able to show with considerable confidence that worms exhibited a preference based on the geometry of an object that they were dragging into the burrows. Getting back to an earlier point, did Darwin prove that worms are intelligent? Well, no, he didn't. He did make an extensive case for worms displaying a preference based on geometry, and this could be attributed to intelligence, however you decide to define it. Generating a mountain of supporting evidence for a proposed explanation is really the best that science ever does. The non-scientist must learn to understand and accept this as the way that science works.